Raf van der Smisse, and we are here on the Xenics booth at SWRI Defense and Commercial Sensing Show in Anaheim, California. Today I would like to talk to you about the key specs for SWIR detectors, namely read noise and dark current. And I would also explain you the influence of these key specs on the main parameters or main performance parameters of cameras in applications. So how will they influence the sensitivity, the dynamic range, and the maximum signal-to-noise ratio? So first of all, the read noise is expressed as a number of noise electrons, and it's a fixed number of electrons per exposure. The read noise generated in the ROIC or in the readout circuit, it can basically only be reduced by using averaging or special techniques such as correlated double sampling. But these techniques will always have an influence on the frame rate of your cameras. Dark current then is very important in SWIR in-gas detectors, which are typically uncooled or TE-cooled detectors. So usually liquid nitrogen cooling or Stirling coolers are not needed for SWIR in-gas detectors. And the dark current is very temperature dependent. So dark current is the current flowing in the photodiode when there is no illumination at all. So it's a leakage current, and obviously it's an unwanted current. It's also strongly dependent on the back bias of the diode. So the dark current itself is not noise, but it generates extra noise. It's the so-called shot noise. So the longer the exposure time that we have in our cameras, the more shot noise that will be created. So how do these specs, read noise and dark current, influence the performance of a camera in an application? Or how do they influence the sensitivity, the dynamic range, and the maximum signal-to-noise ratio? So first of all, sensitivity is directly related to the read noise or noise floor, because it's the smallest signal that can be detected. So if you look at read noise and you divide it by the quantum efficiency of your detector, it will give you the minimum number of photons that can be detected. The dynamic range is the ratio of the maximum signal and the noise floor. So maximum signal is related to the full well capacitance of your detector, but the usable maximum signal will be influenced by the dark current, as it gives you an offset. Similar with the maximum signal-to-noise ratio, this one is defined as the ratio of maximum signal and the total noise. So total noise would be the read noise combined with the shot noise. So the dark current will limit both the dynamic range and the signal-to-noise ratio of your detector or camera. So what do we do at Xenics about read noise and dark current? So first of all, read noise, we do in-house ROIC design. So in Belgium we have a team of readout designers working on low noise ROICs for both 1D and 2D SWIR in-gas detectors. On dark current, we are working on improvements in material quality, improving the quality of the diodes, and trying to reduce the leakage current. We also allow our customers to control the sensor temperature and to control the back bias of the photodiodes for all our SWIR cameras. For example, for the Bobcat camera here, customers can stabilize the sensor temperature to 20 degrees C. If more cooling is needed to reduce the dark current further, they can go to the Xiva camera or the Cheetah camera, as this one here, where you can cool the sensor temperature to 0 degrees C. We also have 3-stage TE-cooled versions of these cameras that allow you to cool to minus 40 degrees C. And for the extended SWIR cameras, the ones that go up to 2.35 or 2.5 micrometer, we work with a 4-stage TE cooler that allows you to cool to minus 70 degrees C.